So now that we've talked about some of the derivatives just of polynomials and how to find some derivatives without having to go through the limit process each time, we're going to start to look at product rules that will work when functions are structured a certain way. So product rule means just that. I'm dealing with a product. So I have a function h at x that's really two smaller functions being multiplied together. So f at x times g at x. The lettering isn't important, it's the structure. So an example of this might look like h at x equal x squared plus 2 times x plus 5. So I have two little smaller functions that are being multiplied together to give me this function. Now, a lot of people want to say, well, those functions inside the brackets are quite easy. So h prime at x might simply be, well, the derivative of the first one is 2x plus 0, because power rule, this derivative is 2 times x to the 1. The derivative of 2 is 0. And then the derivative of this, well, the derivative of x is 1. The derivative of 5 is 0. So that would give me 2x. So a lot of people want to just take the derivatives and multiply them. This does not work, because let's do something that we're familiar with. If h at x is these two things multiplied together, I could FOIL this out to get the same function that looks a little bit different. I'd get x cubed plus 5x squared plus 2x plus 10. All I did there was FOIL. And now, if I apply the rules, the derivative of h, or h prime, would be 3x squared plus 10x plus 2. Not even close to the 10x that you get if you just do the products and multiply them. So the rule is not just take the derivatives separately and multiply them. You can FOIL it out and take the derivatives according to the laws we looked at last one, but there actually is a short form or a rule. So product rule states that if h at x is equal to f at x times g at x, then h prime at x equals f prime times g plus f times g prime. So another way this is read is f is the first part of the function, g is the second part of the function. So you take the derivative of the first, multiply it by the second, plus the first times the derivative of the second. Before I go into the proof, I'm going to go back up and show you how this works for h at x, because we know what the derivative should be. It should be 3x squared plus 10x plus 2. So h at x equals x squared plus 2 times x plus 5. So now, if I apply this is my f, this is my g, or this is my first, and this is my second. So I do the derivative of the first, which is 2x, times the second. So I don't take the derivative, I just grab the second, plus the first times the derivative of the second. Well, the derivative of the second is just 1, because the only part that has a rate of change is the x. 5 doesn't. And now if I FOIL that out, I get 2x squared plus 10x plus x squared plus 2, which gives me 3x squared plus 10x plus 2, which matches what we got at the top. Now, some of you might think this is more work than what we did up here just to FOIL it and do it, and that's true. But there are some instances where these functions are so big that this actually is quicker. But before we do more examples, I want to prove product rule to you. So we have h at x is equal to f at x, g at x. So I just have a product function. H prime is the limit as h approaches 0, h of x plus h minus h at x all over h. Okay, so that's just my definition for the derivative. Now, if I sub x plus h in, I'm going to get f of x plus h times g at x plus h minus f at x times g at x all over h. All I did there was replace the h notation, and actually I think I might change this to a capital H just to distinguish it from this h on the bottom, which represents the distance between our 2 points. But h is just f times g. So f at x plus h times g at x plus h, f at x, g at x. Now, I can't do a lot with this right now because I can't common factor. Just going to have to trust me. I would never expect you to come up with this on your own, but I'm going to add in 0. Remember, we've talked about this a little bit before. You can multiply by 1 no matter what the 1 looks like without changing something. You can also add 0 no matter what the 0 looks like without changing. So this is what my 0 is going to look like. F at x times g at x plus h. So then I have to do plus f at x times g at x plus h minus f at x times g at x. And that's all over h. The reason I did that, and again, I would never expect you to know to do that 0 on your own. But by doing that, these first two things have a g at x plus h common. So I'm going to common factor it out of the first two. So I'm going to take out a g at x plus h, and then I have an f at x plus h minus f at x. The second two have an f at x common. There's an f at x there. There's an f at x there. I'm going to take an f at x out of those two, and I get g at x plus h minus g at x. Well, f at x plus h minus f at x over h is our limit definition. That is f prime. So this part right here is f prime. I'm also going to have a g at x plus h minus g at x all over h as well. So by the very definition, that is g prime. So this gives me the limit as h approaches 0, g at x plus h times f prime at x, because that's what this definition is, plus f at x times g prime at x. Well, it's looking close to what I said, the derivative of the first times the second, plus the second times the derivative of the first. I think I said that wrong. Sorry, the first derivative of the first times the second, plus the first times the derivative of the second. But now there's no more h on the bottom because it disappeared into our limit definitions. So I can put the h equal to 0 there, and this just gives me f prime at x. I move that first, and then I have g at x plus 0, which is just g at x, plus f at x times g prime at x. And that's what we said at the beginning, or I gave you as the rule. Derivative of the first times the second plus the first times the derivative of the second. So let's look at some examples. Find h prime if h at x equals x squared minus 3x times x to the 5th plus 2. And again, there will be times where you might just decide to FOIL this out, clean h up first, and then find your derivative. But I'm going to practice applying product rule. So product rule says I take the derivative of the first, which is 2x minus 3. 2x minus 3 times the second. So I don't differentiate the second part. I leave it as x to the 5th plus 2. Plus the first, x squared minus 3x, times the derivative of the second. Well, now I'm going to take the derivative of this piece, which gives me 5x to the 4 plus 0, because 2 is a constant. And then we can actually clean this up. So I'm going to get 2x to the 6 plus 4x minus 3x to the 5 plus 5x to the 6 minus 15x to the 5, which gives me 7x to the 6 minus 18x to the 5 plus 4x. And I forgot that multiplication right there, so there will be a minus 6, minus 6. Now, when you can't, and we're going to look at this later, so you could expand first and get the answer. But later on, not yet, we will have the ability to differentiate functions that look like this. So I have the product of a binomial and then a root. We don't have any skills to expand this, but we could find the derivative. We're not going to do that yet, but we will get there eventually. So it is important that you do learn product rule, because it's not always going to be possible to find this, simplify it first or expand first, and then do the derivative. Okay, so 2. G at x equals 5x cubed plus 7x squared plus 3x times 2x squared plus x plus 6. You could expand it in this case, but I'm just going to do, okay, g prime is the derivative of the first, 15x squared plus 14x times the second plus the first times the derivative of the second, 4x plus 1, and then of course the derivative of 6 is 0. Then you could FOIL it out, but actually a lot of the times we're going to end up leaving it like that. Another rule we're going to look at is called the power rule. And the power rule is really just an extension of product rule because every power can just be written as a product. So if I have h at x equal to some function, I'll call it g squared. Well, that's the same as g times g, so I can treat it as product rule. So h prime is going to be the derivative of the first, which is g prime, times the second, which is g, plus the first, which is g, times the derivative of the second, which is g prime. Those are essentially the same thing, g times g prime, which gives me 2 times g prime times g. Again, it gets a little confusing. If I kept this going, I could do this out and go g times g times g, apply product rule, and it's going to be fairly long. You can look it up online if you want to see it. But h prime is going to end up being 3. Keep the inside the same, square it, then multiply by the derivative of the inside. So this is kind of like our power rule from before. If there's an exponent, the exponent comes down in front and drops by 1. Whatever's on the inside is going to stay the same. But then we have to multiply by the derivative of that inside. So in general, before I do some examples, if you have a function which is another function to some power n, to find the derivative, you take the exponent or the n down in front, keep everything the same, drop your exponent by 1, but then look inside at what's actually happening inside this bracket and multiply by the derivative of that. So I'm going to do an example. This is actually example 3. So if I have h at x equal to x squared plus 3x plus 5 to the exponent 4. I guess if you really wanted to, you could write this bracket out 4 times and expand it, but that would be a little crazy. If I apply power rule, the 4 comes down and then goes to a 3. So the exponent comes down in front, drops down 1. At this point, you do not do anything inside. This inside function stays the same. And then at the end, we go back and look at this and multiply by that derivative of the inside. So in this case, it would be 2x plus 3. Now the last thing I want to look at is what if we have a combination of power and product rule. So f at x equals x squared plus 3x to the 4 times 2x plus 1. So then f prime at x is going to be the derivative of the first, which is 4, keep it the same, 3, and then multiply by the derivative of the inside. So all of this is just the derivative of the first times the second plus the first times the derivative of the second. Now, we are going to get into a habit of not multiplying this out. We're actually going to common factor.
This is not the bell, please remain in your classroom.
They both have.
Please come see your in attendance. Paul Trudeau.
Sorry about that.
Megan Reed, Max O'Connor Cunningham, Sarah Button, Connor McLean, and Connor Eastoff. Please come to the attendance office.
They both have this bracket, at least to the exponent 3, and they both have a 2 that's common. So I'm going to take out 2 with 3 brackets, and I'm going to be left with a 2, because I had this 4, but I'm common factoring out a 2. I had 3 of these brackets, but I'm taking 3 out, so I'm left with a 2 and a 2x plus 3, plus, okay, I had 4 of these brackets, I'm factoring out 3 of them, so I have one of them, x squared plus 3x, and then I had the 2, but it's still there, so my last step, the only thing I can do is clean up inside the big bracket, which is going to give me x squared, 4x plus 3x is 7x plus 6. So it does allow us to do some work without having to expand things out. Your homework starts on page 145 of your textbook. Take a look at questions 1, 2, 4, actually 4 to 8, and then 10. So 1, 2, 4, 5, 6, 7, 8, and 10. Again, you don't have to do every section of every single question, but make sure you know how to do all of those questions.